Right. Okay, so I guess we'll start the second part of this lecture. And my next, the next person in this story will be again Huygens. Huygens played a very important role in the 17th century. We saw at the beginning of this lecture that he invented the first precise clock. He was an astronomer. He was working in the Observatory of Paris. He was a member of the French Academy of Sciences. In fact, he was a Dutch expatriate, spent most of his life in Paris, except at the end, because Louis XIV revoked what's called the Edict de Nantes, which allowed Protestants to stay in France. And at the end of the 17th century, the Protestants were expelled from France, including Huygens, who wrote this treatise about light, the Traité de la Lumière. He wrote it in French. He dedicated it to the king from Poland, in spite of the fact that he had been forced to leave France. And this is the first real important treatise about light since the doctrines of Descartes. Huygens, of course, knew the velocity of light. In fact, that helped Roller to measure the velocity of light. And he assumed that light was propagating at this very important speed, which is about 1 million times the speed of sound. And he assumed that light was a wave. Light had a wave character. It was an ondulation of this medium, the ether, which was made of very rigid particles. And it was this vibration of the ether which propagated from point to point, which made a light. What a very intuitive and very important discovery of Huygens was the fact that to compute the propagation of light in a medium, when the light reaches a front, when you have this, the front of the wave coming to a point, each point on this point can be considered as a source of a secondary wavelet which propagated light further. And the next wave front was made of the envelope of these wavelets. And in this way, you can compute or you can estimate how light will propagate from point to point. This is called the Huygens Fresnel principle because it was further developed in a mathematical form by Fresnel in the 19th century, and we will see that next week. So you see these kind of pictures on the top of this slide. You see one particle of ether which pushes this one, and this one in turn which pushes 3 particles and so on. This will propagate further and further. You see here how he described, assuming that you have a diaphragm, that you limit the light propagation in a small solid angle, light will propagate in this solid angle using this principle, and this trying to explain this way the propagation of light in straight lines, in spite of the fact that it was a wave. He was not able to do it quantitatively because he did not know the diffraction theory. Diffraction theory was intuited by Grimaldi in the 17th century, but was proved in a mathematical way by Young and Fresnel in the 19th century. So this was just a preliminary statement. What Huygens, this principle provides a geometrical model which allowed Huygens to explain the reflection and the diffraction laws and the linear propagation of light, and also he allowed him to deduce Fermat's principle from this kind of model. So on the next slide, I show you the figures which illustrate in the Traité de la Lumière how light works. At the bottom of this slide, you see a drawing in which Huygens explains that light is reflected according to the well-known reflection law. So it's not very clear on this picture what happens that you get a wave which is coming from the left. The wave front reaches first this point, then this point, and that point, and each of these points is a source of a secondary light beam whose wave fronts are circles that you can see here. If you take the envelopes of these circles, you find the reflected beam going at the right angle. he also used that to demonstrate the sine law of refraction. This is a picture made by Huygens. Since it is not very clear, here I replace it by this more modern picture which shows the same thing. What you see here is that the light ray arrives like that. Each point on the surface is a source of a secondary wave, and that sometimes this wave has had more time to develop than that wave and so on. And the envelope of this wave did the refracted light. And the important fact is that the distance between the light fronts are smaller in this medium than in air, which explains why the light is refracted inside the medium. And this is due to the fact that light is going slower in the medium than outside, which is opposite to what Descartes had said. The last picture here is a picture which I won't enter into the detail, but this explains how Huygens used geometrical arguments to find Fermat's theorem. The blue paths correspond to the sine law, and what he shows is that all the passes that you can think of which are shown in blue are longer, take a longer time for the light to propagate. And he compares the length of this time by using the Pythagorean theorem. He pits rectangle triangles everywhere, and he's able to make a geometric demonstration of Fermat's principle. Huygens had another very important contribution to optics, which is the first study of the anisotropic media, which have a double refraction, which one beam coming in gives rise to two beams inside the medium. In fact, this was discovered by chance. Some traders coming from Iceland brought back to Europe small crystals, which was called Icelandics, which had this property. If you look through this crystal is a kind of rhomboidal shape. It's a parallelepiped in which you have squeezed two opposite sides, so it has a rhomboidal shape. If you put it on a piece of paper and look, for example, across, you see two images of the cross through it. One beam is going straight across the medium, which obeys the Snell's law, but the other beam, when it enters into the medium, is displaced laterally and gives rise to the extraordinary beam. So Huygens started to study that, and what he found is that if you have two crystals which are oriented in the same direction, if the ordinary beam is going through the first crystal, it will go again as an ordinary beam through the second one. But if you turn the second crystal by 90 degrees, the ordinary beam in the first medium becomes the extraordinary beam in the second one. So he discovered in this way that light has a transverse property. It is not invariant by rotation around the beam. This transverse property now is known as polarization. And the properties of polarization were studied in more details in the 19th century, and I will talk about that next week. But Huygens had the intuition of that, and he had the intuition that this media propagated light with two different velocities, giving rise to two different indices of refraction, depending upon their polarization. So it was a very important discovery. So I just insist that I think Huygens is certainly one of the major physicists of the 17th century for these discoveries. Now I have to come to the great opponent Huygens, which is Newton. Everybody knows Newton's contribution to mechanics and to gravitation laws, but Newton was also interested in optics, and he wrote a treatise, Optics, which was published at the beginning of the 18th century, but which summarized the work that Newton had been doing years before, at the time where Huygens was also working. But Newton had exactly the opposite view about light. He says, and I quote here, this is query 29, rays of light are very small bodies emitted from shining substances. So he assumes that light was made of particles. And he said that particles must have very special properties because when they enter into a birefringent medium, one side of the particle should have a property different from the other side. So he compared this to magnetism. It was very, very qualitative, and he said that there are some difficulties about that. But he still assumed that light behaves that way, and this has a very important consequence for refraction. because it is the same model as Descartes. It means that if light is a real particle, it has to be faster in the medium than in air. And Newton said, okay, the medium is heavier, so it attracts more particles than air, and explained why the particle is deflected normal to the surface. So this was a theory which was completely opposite to Huygens. And you had, in fact, two competing theories starting from the year 17. All the 18th century. Huygens, which says that light is a wave, which goes slower in a transparent medium than in air, and Newton, who says the opposite. Light is a flux of particles which go faster in the medium than in air. There was a contradiction here, so one of them had to be wrong. And of course, there was a very clear answer. To answer, one had to measure the velocity of light in the medium. But of course, nobody had done that, because the only measurement of velocity of light were done by astronomical measurements. There is no way to feel the universe with water to see what happens. In fact, one had to wait until the 19th century. It was the first measurement of the velocity of light in a lab to check, and we'll see next week that indeed light is going slower in water than in air. So Huygens was right, Newton was wrong about that. But we have to wait to find the solution of this contradiction. But this is not the only contribution of Newton to light. In fact, Newton made the first theory of colors. And this is, of course, the reason why he's well known about optics. He found out, as you know, that the white light of the sun can be dispersed by a prism. So he made a small hole in the shutter in the room, the obscurity of the room, and he found on the opposite wall that you had a spectrum of colors going from blue to red, kind of rainbow. And he understood that was due to the fact that the refractive index of the medium depends on the color. And what he found, that the blue being more reflected than the red, he assumed that the blue light was going faster than the red light. Of course, we know now that it's the opposite. But still, he understood that the relationship between colors and refractive index. Another contribution in the same domain was the study of the colors of what is called Newton rings. When you put a lens, a concave lens on a flat surface, the distance between the two diopters varies with the distance to the contact point, and so you get rings of various colors. We know now that these colors are due to interference effects. The light is reflected back and forth between the two mirrors and gives rise to colors when the multiple of the wavelengths correspond to the gap. Newton could not explain that because he had a particle vision of colors, but he described very precisely these spectra. And when in the 19th century Young took back Newton's papers, he was able to compute the wavelengths of light from Newton, in spite of the fact that Newton didn't believe in that. And Newton tried to explain that by saying, depending upon the width of the gap, the particles get fits and starts, decide whether they should reflect or bounce, depending upon the distance they have to travel. So it was not a real explanation, there was no calculation, but he tried to relate, to find an explanation for the colors in the particle description. Another big contribution of Newton was the invention of the reflecting telescope. We know that the Galilean telescope was a refractive device. Light was going through glass. In Newton's telescope, the light is staying all the time in vacuum or in air, and this has many advantages. First, the reflection laws are independent of color, so you didn't have any chromatic aberration. If you look through a Galilean telescope, the various colors are focused at different points, and you get a blurring effect due to this mixture of colors. In Newton's telescope, there is not such an effect. Another improvement is the fact that his surface of his mirror was not a sphere, it was a parabola. Because a parabola is the surface which reflects a parallel beam into a single point. This is a consequence of Fermi theorem. It's related to the fact that the parabola is a locus of points which have a constant distance between a very far off point and the focus. It does not depend on the position of the reflection point in the parabola. So using parabolic mirror, he eliminated the spherical aberration, the fact that the sphere has aberration, does not focus on this specific point. And the third advantage of this kind of telescope is also that you can make huge mirrors. And the size of the mirror gives the resolution because of diffraction laws, which are not known at Newton's time, but which tells us that the biggest the mirror, the smallest is a point, the image with which we can resolve an image. And this explains why, since then, the most powerful telescopes are using the Newton device. In fact, the light is focused at the focal point, and then you have a mirror at 45 degrees, which sends the light to an eyepiece on the side, through which you can look or take pictures. And all the modern telescopes are using this device, including the one which has been launched a few weeks ago in space. It's a big parabolic mirror which is developed, and of course it's much mirrors than to make a big lens, which would weigh tons in the decade. So these kind of mirrors are much better for astronomical observations, and this is one achievement of Newton. The last point I would like to make here is to come back to the velocity of light. In fact, I led you with the impression that this measurement was very poor. In fact, Romer's precision was about 30%, 230,000 kilometers per second, and the big improvement was made by Bradley, an English astronomer in 1729. He realized that if you look at the star over a year, the star is not always at the same place. The star is making a very small circle or ellipses in the sky. And this is due to the fact that the Earth is moving with respect to the velocity, to the rate of light. In fact, you have the ray of light seen from the moving observer is inclined at an angle which is different from what it is in the reference frame of the Earth's orbit. And it is quite clear that, in fact, the light is inclined by an angle which is the ratio of the velocity of the Earth around the Sun divided by the velocity of light. The light velocity is 300,000 kilometers per second, and the velocity of the light around the Sun is 30 kilometers per second, so there is a factor of 10 to the 4. And so the angle by which the direction changes over the year is 1 part in 10 to the 4, which is 20 arc seconds. So by a very precise measurement of the order of the precision of about 1 arc second, Bradley made this measurement and find out the velocity of, again by an astronomical measurement, by the aberration of stars, find the velocity of the light. And he said that he used English units and said light propagates over 500 billion feet, which is the diameter, the radius of the Earth's orbit, in 8.5 minutes. This corresponds to 295,000 kilometers per second, which is the right result within 1 or 2%. So it has improved by a factor of 10 and 20 the precision of Romer's measurement. And this was a measurement which was used in the 19th century by Thomas Young. We'll see that next week. And it had been improved only at the end of the 19th century by measurement performed on Earth. Just to show you here an illustration of this aberration effect, which I have experienced myself. Suppose that you have a convertible car. The car is sitting still, and the rain is falling vertically. Of course, you get wet, and the seat gets wet, it's very uncomfortable. On the other hand, if you drive fast enough, you see the drop of rain falling at an angle, and if the angle is big enough, you are protected from the rain by the windshield. So and this works. I can tell you that if you run fast, if you drive fast enough under the rain, you are not wet in this case. Of course, the problem is that you cannot stop, and you have to run fast enough. So it's much better to put a top in the car, but this is the aberration effect. And people were thinking that Newton was right against Huygens, said, look, the rain is made of drops, and you understand the aberration effect by assuming that light is made of particles. But this is not a proof because this effect occurs also with waves. So there is no way to distinguish wave and particle theories by just using taking the aberration effect into account. So I came here almost at the end of what physicists and what scientists have understood about light until the end of the 18th century. But I want to tell you here another story which is related to that, and which shows you how all parts of science are related. And I want to talk about an interesting study which was done in the 18th century, which is the study of the shape of the Earth. And you will see that there are some connection with the study of light. But the problem is the following. The ancient, nobody knows all the physicists knew since the time of Fermi, since antiquity, that the Earth was a sphere. And it was assumed that it was a perfect sphere. Why? Because the perfect sphere is the most symmetrical shape you can think of. So God or nature should make sure that the planet should be a sphere. But there have been signs starting in the 17th century that the shape of the Earth should depart from that sphere. And I want to tell you this story because it tells a lot of interesting things about science and discoveries, which are still valid today. In fact, we have to come back to the character that I mentioned already. Jean Richer was a guy who went to Cayenne to measure the parallax of Mars. And he brought with him a Huygens clock. And he was surprised to find out that the clock was running slower in Cayenne than in Paris. The clock was late, and it had a delay of about 3 minutes per day, which was huge compared to the 10 seconds per day of the precision of the clock. It was about 15 times more than the error coming from the precision of the clock. So he was intrigued by that, and he stated that the clock was going slower. And he said, of course, he informed Huygens. And Huygens understood very quickly that it was due to the centrifugal force. Huygens discovered that a rotating body like a merry-go-round, when you are on the merry-go-round, you experience the force which pulls you away from the rotation. Force is proportional to the square of the acceleration, omega square, and is proportional to the distance from the rotation axis. And this is well known from Newton's law. So this force is acting against gravitation. When the Earth is rotating, it subtracts from the gravitational force, so it decreases the gravitational field from what you could expect. And it does it more at the equator than at northern latitude, because equator is further away from the rotation axis than higher latitude. This problem is connected to Galileo's ideas about inertial frames. You know that Galileo had understood that if you move with a constant velocity, no extraordinary physics will tell you whether you move or not. But the Earth is not moving in a given direction, it's rotating, and the rotation motion has an acceleration. And so you can perceive whether you are in a rotating body or not by precisely measuring this force, which is pulling you away from the rotation axis. On this slide, I just give you a very simple calculation that I let you do because it's a note. You can compute this force, the resulting gravitational attraction, by projecting it along EZ, which is the direction of the polar axis, and EX, which is perpendicular to this axis. You see that in Paris, you have the resulting force is shown here, and in Cayenne it's shown here. So there's a difference. Of course, I have exaggerated a lot the centrifugal force, which is 1/1000 of the other force, but just to show you how it works. And then you can very easily, using the Pythagorean theorem, compute what is the effective gravitation at a given latitude. So you see here, at altitude theta, you have one component of gravitation which is proportional to cosine square to cosine theta here. You have to subtract the centrifugal force, And then you have a component of the gravitational force along EZ, which you project in this direction. Then you compute the magnitude of the gravitational force by Pythagorean theorem, the square root of the two components, and you expand it and you find this result. You find that the gravitation is reduced by a factor which is proportional to the cosine square of the latitude. So it's a very simple calculation. Then you have to take into account that the period of a pendulum is inversely proportional to the square root of G, and you get a very simple estimate, which is shown here, that in Cayenne the period should be longer than in Paris by a ratio which is about 1.5 part in 10 to the 1,000. And 1,000 of 86,000 seconds, which is 1 day, give you 80 seconds, 83 seconds. And so by just this effect, you expect a pendulum delay of about 1.5 minutes. So it's part of the answer that you still see that the real difference is about twice larger. So there is still something which is missing in this kind of argument. And what I want to say at first is that this experiment is an illustration of Galileo's ideas. And I remind you the discussion that Galileo has in these dialogues concerning the two-sheet world systems. He discussed in discussion between two people, and Galileo says, if you are in a ship, in a boat, and the boat is still, you drop a ball or you drop some liquid into your cup, it will fall vertically. If now the boat is moving at a regular speed, you will see exactly the same thing. So there is a relativity of motion. You cannot see whether you move or not. And this was an illustration of the fact that you could not decide whether the Earth is moving or not. And this was against the thought of the church, who said, of course, the Earth is motionless because we don't see the motion. But Galileo said it's not an explanation. You would not see the motion even if the Earth is moving. On the other hand, if the Earth if the boat is not moving regularly, if the boat has an acceleration, for example, if you are pitching forward or backward, or if it's rotating, then you will see. And it's exactly what happened in this experiment. Richter was the first man on Earth who realized that we are not in the Galilean, that the Earth was not a Galilean frame in other ways than just looking at the stars, but just to look at this pendulum. And of course, there is another very famous experiment which shows the same thing, which is Foucault's pendulum in the 19th century, which shows that the plane in which the pendulum is oscillating varies with time. Foucault is a character that will be next week because he's the one who measured the density of light and found that it was slower in matter than in air. So we see that all these problems are more or less related, and I wanted to describe that. So the question remained that the effect was larger than the direct effect of the centrifugal force. And then Huygens and Newton thought about the problem again. They said, well, if there is a centrifugal force, this force should have changed the shape of the Earth. Because at the beginning, the Earth was made of malleable liquid substance, and by rotating, the matter at the equator would be pulled away. And so the Earth should be an oblate, not a sphere, but an ellipsoid, which is bulging at the equator and flattened at the pole. So this was Huygens and Newton model, and they even computed the ellipticity which was resulting from this. And this, of course, would help because at the equator, the pendulum was further away from the center of the Earth, the northern latitude, and this effect would add to the centrifugal force they computed and would explain the spherical effect. But there was a competing thought. The Cassini was the astronomer that I talked to you about last hour. And the Cassinis were very powerful. Cassini, father and son, and grandson, they were all royal astronomers in Paris. They had a lot of influence. And they believed that it was the opposite, that the Earth was not an oblate ellipsoid, but was a kind of, instead of being like an orange, they were like a lemon that was pointing toward the pole. Why were they thinking that? Because they had been asked by the king to make measurement, they map France, and they mapped it by triangulation. They used telescopes to make triangles in the ground, to measure with precision the angles of triangles, to measure one base by having a stick which is reported on the ground. And from that, they made a map of the north and the south of France. This map has many consequences. First of all, the king was not very pleased because he found from these maps that his state, his territories were smaller than expected before. So he used to joke by saying that the Cassini's had reduced his realm much more than all the walls it had made. So he wasn't pleased about the Cassini's about that. But the Cassini had also found that the 1 degree of latitude difference in the north of France was smaller than 1 degree of latitude in the south of France. And this was pointing to the fact that the Earth should be an oblong, not oblate, but oblong solid. So the two theories were competing, and the French Academy of Sciences decided to do an experiment. Check that. And so this is a text that Maupertuis, who was a member of the Academy, wrote in an article, and I translate this in English because it's very interesting. So he said, the Academy was thus split on this issue, which is the oblateness or prolateness of the Earth. Its own lights on this question have left it unable to decide. When the king expressed his will to resolve this big question, which was not one of the vain speculations whose idleness or useless subtlety sometimes keeps philosophers busy, but a question which must have real influences on astronomy and navigation. I think this sentence is important because it shows that already in the 18th century, there was a conflict between blue-sky research and applied research. Blue-sky research costs a lot of money. Here you have to send expeditions to measure 1 degree of latitude in the North Pole and equator. And it's supposed to be something which is idle, which has no usefulness. And Maupertuis had to explain that it would be useful because knowing the shape of the Earth would be useful for astronomy and navigation. And still nowadays, when we try to do an extensive experiment, we have to try to explain that it's not only for knowledge, that it might also be useful. And this was already the case at that time. So one team was sent to Lapland. It was Maupertuis himself and Celsius. And another team was sent to Peru. It was Lacondamine and Bouguer and many other people. And they were asked to measure 1 degree, the distance corresponding to 1 degree of latitude difference on the meridian near the equator and near the pole. And the idea was simple. The Cassini had measured the difference between 2 points which are too close to each other to make sure there were no errors. If you accumulate the difference between the pole and the equator, the difference will be larger than the errors, and then you will know the answer. What I find fantastic in this experiment is how much it cost. You see here the travel of Lacondamine. It took him something like 11 years to complete this task, so he left France, he sailed to Cartagena in Colombia, then he had to go by boat on the Magdalena River and then down to Quito in Ecuador. He spent 10 years measuring the meridian here, then he came back through the Amazon River, went to Cayenne, then to Paramaribo in Suriname, the Dutch Guyana, found a boat to bring him back to Amsterdam and then to Paris. Took 11 years, he risked his life many times. Members of this expedition died, there were a lot of adventures, and Bouguer and Lacondamine came back with the result of the measurement. So what was the result? First of all, this shows the triangles that Lacondamine and Bouguer studied. This is the valley between two Andes, two mountain ranges in South America. Quito is in the north. I'll show you on the next slide. You start from the equator. You see Quito here, just south of the equator, and you see the Cotopaxi volcano, which is halfway between Quito and Cuenca. And they paved all this way with triangles. And they used telescopes to point to the tip of the mountain or to the tip of of the church power, and they made triangles. But of course, it's not enough to make triangles. To get the scale, you have to measure at least one side of these triangles. So they are brought with them sticks, which are called in France, it's them toises du Pérou, sticks which were used in Peru to measure the meridian. And they had to hire Indians to carry the sticks, they had to get in connection, in relationship with a lot of Spaniards, not only also soldiers and a lot of adventures. And in the end, they were able to make this measurement. I show you this map because near the Cotopaxi volcano, there is a farm, a hacienda, which I have visited about 10 years ago, in which Bouguer-Lambert had stayed in the year 1742. And there are still remembrance of Bouguer-Lambert staying in this area. We will talk to you about that. So the result was two reports to the French Academy of Sciences. One report which was made by Bouguer, who came back before Bouguer-Lambert. So the title of his report is a short report about the voyage made in Peru by the gentlemen of the Royal Academy of Sciences to measure the degree of the meridian near the equator and deduce from it the shape of the base. And a few years earlier, because the trip of Maupertuis was shorter, Maupertuis had also reported about his measurement near the polar circle. So the shape of the Earth determined by the fellows of the Royal Academy of Sciences who have measured the degree of the meridian at the polar circle. And when you compare the two, the Earth is oblate. So the difference between the equatorial and polar radius is about 3 parts in 1,000. This explains the difference of the pendulum periods, and the value is close to the ones which were calculated by Newton and Huygens. So it was a big, interesting result. In fact, Voltaire was a big enemy of the Cassinis. Voltaire didn't like the Cassinis at all. So when he learned about this, he sent a letter to Maupertuis and told him, congratulations for having flattened the Earth and the Cassinis. So it's part of the story. And I just add that when I was in this hacienda had become a hotel, very nice hotel in the middle of these mountains. And there is a plaque which is there by the French Academy of Sciences, which recalls the fact that Bouguer-Lambert visited the place in 1742 and observed there an eruption of the Cotopaxi volcano. So he had done a lot of other observations than just measuring the meridian. And Bouguer, who was traveling with him, did another interesting measurement. He carried a pendulum and he walked up the volcano to see that the plane of the pendulum was decreasing with altitude, which is another effect due to the distance from the center of the Earth. And in fact, when you visit these countries, the people there, the Ecuadorians, are very proud to say that the summit of the Chimborazo volcano, which is 6,000 meters above sea level, is in fact the highest point of the planet. Because not only it's a big mountain, but it's on the equator, and so it's further from the center of the Earth than the Everest, because of this latitude problem. So this was an interesting measurement. I want to finish by saying a few more words about Bouguer, Pierre Bouguer, who spent 10 years of his life, wasting his life in the Andes, was a big specialist in optics. In fact, he was the father of photometry. In fact, up to now, I have considered the geometry of light rays, the propagation of light, but there is another important problem, is how to measure the intensity of light, and how the intensity of light depends on the direction in which you make a measurement. And Bouguer did interesting discoveries about that. He invented several interesting devices. For example, this is an apparatus which was used by Bouguer to compare the luminous intensity of two screens, which are illuminated by a candle, and the light is going directly to the eye on one pass and going to the eye through the medium, a transparent medium, the other pass. And of course, light is attenuated in this transparent medium, and how to find how much is attenuated, you move away the screen in the free path, and you move it away until you see the two intensities the same. At that point, you know how much the intensity has been decreased if it's one over square R and so you can compare intensities in this way. So this was one apparatus. Another apparatus which is shown here is an apparatus which is used to see how the intensity varies with angle. So you have two arms, one arm which has a fixed length, and the other arm has a sliding path, and so you can increase the length of the other arm, which decreases solid angles in which you see light. And then at the other end, you have two small bits of paper, and you can compare the intensities of the two arms, and so you can see how long you have to make this arm in order to make the two intensities equal, and so you can see the angular variation of the intensity. And what Bouguer found is that if you illuminate a flat surface with light, the intensity that you see depends on the angle with a cosine theta law. So you have less intensity per unit solid angle in an oblique direction than in the vertical direction. It's called the Bouguer-Lambert law because Lambert is the physicist who found this. And Bouguer, in fact, corrected the error, the wrong statement which were made before. There are certain people who said the intensity is the same in all direction. And Bouguer said, if you say that, it means that if you look at the solar disk, it should be much brighter on the side than on the center. And since the solar disk is uniformly bright, it means that the Lambert law, this law has to be valid. And he gave this explanation, which I show you on the right side of the slide. You see here, for example, this is the sun or the moon, and you take a small unit disk area at the center, and you take the same unit disk on the side. You see that if you go on the side, the surface appears to be decreased by the cosine theta factor. So if light on the side was sent with the same intensity in all directions, the light on the side would appear brighter per unit area. And it's because you have a cosine theta which appears for the surface and in the decrease of intensity with angle that you get a homogeneous illumination, not only in the center but also on the side. So Bouguer made the measurement and also he used this general result to find out what was going on. So I summarize at the bottom of the slide Bouguer's discovery. He confirmed the fact that intensity decreases as 1 over r squared, which is something that Kepler had already noticed a century before. He found that transparent media attenuates in a ratio which is proportional to the thickness, which means that the light is decreasing exponentially with the thickness of the transparent medium. It's called the Bouguer-Lambert law, and he discovered this cosine theta factor, which is important in photography. So this is about the end. I just finish by something which is not directly related to light, but which is another measurement of a very important parameter of the Earth. At the end of the 18th century, Cavendish, an English physicist, measured the gravitational constant G with Newton's law, which is the mass of the Earth. And this is another important parameter. We have seen that physicists have been able, scientists have been able to measure the radius of the Earth to find that the Earth is oblate. Another very important parameter is the mass of this big solid. And this is given by Cavendish experiment, which I recall you very briefly here. There is no way to know the gravitational constant from astronomy because we don't know the mass of the sun, the mass of the planet. So Cavendish did an experiment in the lab. He used two big masses which were influencing the motion of these two small masses which were on a horizontal rod suspended to a torsion wire. So this wire has an equilibrium position, and if you do the experiment, the wire will turn by a small angle when this mass influences this mass and here, and this mass influences this one. So you have a rotation, very small rotation, and you have to be very careful because maybe air draft will completely perturb the experiment. So Cavendish did a very precise measurement, and from that he measured the force. He knew the mass, the two masses, small m and capital M. He knew the distance. So the only unknown was the gravitational constant, which he got from this measurement. And then, knowing the acceleration of weight falling in the gravitational field of the Earth, and knowing the radius of the Earth, he got the mass of the Earth, which is 6×10⁻²⁴ kilograms. And with the same experiment, he got also the mass of the Sun, which is 2×10⁻³ kilograms. So this was a very important measurement. And one reason I show it here is the fact that this torsion pendulum was used also at the same time by Coulomb, who measures the force between electric charges. And this is an important experiment which will connect optics to electromagnetism, and we see that next week. So this kind of very subtle and very precise and very sensitive instrument played a very important role at the end of the 18th century. So I think it's time to conclude. And then we like to stress what this history of light in the 17th and 18th century has revealed about the permanent features of modern science, modern scientific research. First of all, I remind you again the importance of the link between basic science and technology. The first quantitative discoveries about light required the invention of novel measuring devices, which were the telescope and the clocks. The importance of quantitative precise measurements. It's not enough to have a telescope and to have a clock. They have to be precise enough. And all these experiments require to have a clock which was at the precision of 1 part in 10⁴, 10 seconds per day, and telescope which are able to resolve 1 arc-second, which is a very small angle. 1 second is 1/60th of 1/60th of 1 degree. So it's a very small angle. So you need to have this resolving power and this precision. 1 part in 10⁴ for the time, and 1 arc-second, which is a gain of the order of 1 part in 10⁴ for the angles. Another feature is that the physics has invented simple model to explain disparate and complex phenomena. And an example of that is the Fermi principle of time, which is a simple statement which explains a lot of phenomena which are not directly related and which have to be explained by a single unifying model. I want also to stress the role of chance and serendipity in all of this. For example, Galileo failed in his experiment to measure the velocity of light, but independently from that, he invented the telescope and the pendulum, and these two devices combined allowed the measurement of the velocity of light 70 years later. So he did not invent them to measure the velocity of light because he had forgotten about this problem, but this was used later on to do this measurement. Another example is the fact that Richter went to Cayenne to measure the parallax of Mars, and quite by chance he discovered that the gravity was different at the equator and depends on latitude. These features will again be illustrated by the revolutionary advances of the science of light in the 19th century, as we will see next week. So next week, my lecture will start with Thomas Young and Louis Chantanel at the beginning of the 19th century, and will end with Maxwell's theory of electromagnetism at the end of the century. A lot of problems will be solved during the 19th century, but also very puzzling questions will remain open, which will lead to relativity and quantum physics. So it will be a transition between classical physics, as I studied today, and the modern physics, which will be the topic of the lectures in 2 students. So I thank you for your attention.